You know the title of the talk, it was the Crisis in Cosmology. So I'm going to attempt to explain it from my sort of interested amateur, but with some PhD experience sort of perspective. PhD experience is in astronomy, and it was the atmospheric chemistry, for those of you that don't know. I've still got to let a couple of people in here, so that's all right. And yeah, it makes sense to just wait until everybody's in, doesn't it? But yeah, so a lot of this is me just getting really interested in things on YouTube and going down rabbit holes, which everybody does these days. It's based on that, so I've done a lot more research beyond that, and actually I've got references. I've even got all my reference lists there as well, just for my own joy, really. So a lot of it is a credit to PBS Spacetime, which is a really good, fun YouTube channel. There's an Australian chap called Matt O'Dowd, and he put this across first. He was the first to kind of pick up on it.
Shoot up like you wouldn't believe.
We've got a couple of people not on mute, I think, at the moment. Have you got? Can you still see the background properly? I'll try and minimize the zoom there, so there's just one. Sometimes people are seeing the wrong screen, but have you all got a view? If someone can unmute and just tell me if you can see that all right.
Yeah, that looks perfect.
Yeah, I can see it fine.
It looks great then, yeah.
Right, there we go then. Now I can.
Fine. Yes.
I'll get a notification if someone else wants to come in, but they're the stragglers, aren't they? Right, better make a start. So yeah, it's simple to state this Crisis in Cosmology. It's related to the pictures you can see in the background. The big oval, it's not actually oval at all. It's like a world map in a certain projection. I can't remember the name of the projection now, but it's a projection of the entire sphere, the 360 degrees of the sky around you, much the same as a globe is viewed from the outside. That's viewed from the inside. And that's the microwave background radiation. And that's one half of the talk. That is the radiation that proved the Big Bang existed. So I could start the talk by telling you about, discovery of the Big Bang. Everyone knows, that's the Big Bang theory. There's been a comedy program about it, hasn't there? So common knowledge these days. But you should always be skeptical about things. You never know. There's some crazy theories going around, and there's never 100% evidence. There's no such thing as 100% evidence. Something. So this crisis, it's basically about the Big Bang and the history of the universe's expansion, the rate of expansion of the universe. The other method of measuring the expansion of the universe is by looking at the galaxies. Now that's the bit on the lower left of the screen, where you can see a very deep space telescope image, STSCI, which is Space Telescope Science Institute. That's Hubble, which is the only space telescope really that does optical images at the moment, I think. James Webb is to come, hopefully launching late this year. Got to talk about that, that's another thing. But you can see all these stars and galaxies and crazy arcs, and that's how we can measure distance, by looking for supernovae in the galaxy. And that little inset there with the arrow, which looks like my mouse pointer, but that's my actual mouse pointer. That's a supernova of a particular type. You can follow that over days. If you look for long enough, you'll see these things in a real distant universe, and that's the before and that's the after image. And you can use that to work out how far away that galaxy is. You can then measure the redshift of that galaxy, and that tells you how much the universe is expanding away, and you can calculate the expansion of the universe. also the microwave background radiation has a massive redshift on it. In fact, it's so redshifted that it started out as white light from a plasma when the universe was about 3,000 degrees C. And it's been redshifted all the way through the infrared, all the way to the microwaves. That's why it's called the cosmic microwave background. So this is all about understanding the history of the universe. So I could start with microwave background. That's Penzias and Wilson, or I could start with Hubble, because that's the guy who, you know, gave the name to the Hubble constant. It was quite a sort of larger than life character. I mean, he liked to take credit for things, as you might hear a little bit later. Or I could start it with Albert Einstein, because he came up with the general theory of relativity and he understood gravity. And so far that theory's not been knocked. Or we could just start with God, you know, the creator. Why is this universe so complicated? That's my plea to God, oh creator. So let's get into the meat of the talk then. So there was the Big Bang. You missed it. You missed it, didn't you? Just let Darryl in. So there was a Big Bang. It's indescribably big, but it led to this: galaxies. There was a plasma, as I said, where this incredibly bright light was emitted. There was oscillations in it. Lots of things to study in that cosmic microwave background radiation that we see now. But that led to the seeds of the galaxies, and it all collapsed down because of gravity while expanding. That's the thing you've got to get your head around. This thing was expanding at quite a large rate, not to be confused with inflation, which is another theory, but this is just the general expansion of the radius of the universe. That's also different to the radius that we see as well, because the universe can be way bigger than just the bit we see. Because the cool thing about the universe is when you look out at it, you look back in time, don't you? And that's the most striking thing really about this whole subject, is you're just looking out, and the further you look, you just get a lovely little distance time relationship, and you can just look back in history with light. Just the light arriving has taken longer and longer from the distant objects, and you just get a beautiful ability to trace the exact path the universe has taken. You can work out so much from that. So you'd think everything would be known to a kind of really high level of precision now, given how deep Hubble can look. Like this image has got galaxies. I think the little red specks there and there. There's one of them that's only recently discovered in this image. They're not hot pixels. They're red specks. They're galaxies that are 13 billion light years away. They might not show up on your monitors, depending on the zoom resolution. So galaxies assembled, and now they're fairly sure that these galaxies are now accelerate. The whole universe is accelerating again, which is a really strange thing. So if we jump forward 14 billion years or so, let's get into the sort of scientists of the 20th century now. This is where I'm going to start. I'll cut out all the bit before this, all the astronomers before this, and we're going to look at Einstein. So here's Einstein, and he says, "Zeig mir Ihr bestes Universumsbild, bitte." To all his scientists, that's the German. Your most accurate picture of the universe, probably because he would have said it in German. That's why I'm being accurate. And it wasn't a very good impression of him. Of course, this was while he was developing his theory of general relativity in leading up to 1915. And it was a real struggle, obviously, because he was cutting edge at the time. He knew what he wanted to do, but he couldn't put it down in the form of maths. And he needed to know what the universe was like in order to come up with a theory, because he had to ask all of his observational colleagues to say, look, what does the universe look like? I've got to explain this thing. And they all told him this: it's static. That was the consensus then, so he went with it. You know, whatever that means there's some sort of energy bubbling up in the gaps in between the galaxies that keeps everything kind of somehow in a dynamic equilibrium. So new things were forming in the gaps, and it was all kind of expanding and bubbling, or it was just sitting there. He didn't really, think he trusted his colleagues, and so therefore he had to come up with that equation. That's the first equation. It's a real pig of an equation, but you saw it last month if you came to the talk then. This is his main equation of general relativity. R mu nu minus half R G mu nu plus lambda. That symbol there is lambda, capital lambda, which sounds really nerdy, doesn't it? G mu nu is 8 pi g over the speed of light to the power of 4 times T mu nu. T mu nu is the stress energy momentum tensor. That contains everything about the energy and mass of the universe on that side. And in fact, it's a matrix, 4x4 matrix. So this thing's got 16 individual equations, but it's symmetrical. So it's actually only 10 of them that count. And it's the same R mu nu, everything with the mu nu Greek letters there, means it's actually a 4x4 grid of equations. So it's a serious equation. And I've split it up. It's R minus half R. The R stands for Ricci, the Ricci curvature, which is all about the curvature of space-time. So it's a really cool equation. Just going to show you it again to see what that's like. So we came up with this lambda constant, and it's still used today because there's not been a better theory of the universe. So that's really the start of this whole model of the universe. Something had to be, it had to be based on something, and it's based on that equation. And then we come on to Hubble. So here's Hubble. Hi, I'm Edwin Hubble. I need a pipe for this. The history of astronomy is a history of receding horizons. That's my Hubble impression. Terrible. There he is sitting in 1937 at a 100-inch telescope that he used. He used the biggest telescope, this 100-inch, in 1923. And that was another crucial time in history to first identify variable stars in the Andromeda galaxy. And that's his plate that he took on that telescope. You can see he scribbled VAR, variable. And he wrote all over the photo. I'm quite annoyed at that. We'd never do that now. We'd leave the photo blank, wouldn't we? But I guess it made sense at the time if he was kind of working hands-on. But those little things, the little lines he's put in there, where he's marked out stars. This one here, he's discovered its variable. So then he thought, hang on, I know a bit about variable stars. I know how fast they're supposed to oscillate and how bright they're supposed to be. So he used what he knew in science to come up with a distance, and he realised that for the first time that smudge on the sky wasn't just another nebula in our star-filled universe, but it was actually out beyond into blackness for huge distances of just nothing. And it was another island universe. And so he'd split the universe up, that crucial observation of that one star, suddenly gone from the universe filled with stars to like you imagine in Star Trek, to something where you get a galaxy and then nothing, and then another galaxy and another galaxy, and each one inside each galaxy is like an island universe. So that's quite mind-blowing when he discovered that. But he wouldn't have been able to do that if it weren't for this woman, Henrietta Swan Leavitt. And I can't really do her accent. I've seen so many stars as a computer that the Cepheid law just popped out to me. So that's Henrietta Leavitt. And she was a computer at Harvard. And she catalogued brightnesses of stars. She was assigned it as a job, as a computer. I'm going to give you some data. Crunch the data for me. And she'd actually started that in 1908. This is way before Hubble. I mean, she was doing the pioneering work that allowed all this to happen. So she was almost onto it, 15 years before Hubble. But she didn't, nobody had big telescopes. Hubble was the only one who had a 100-inch telescope. I mean, everyone had up to like 20, 40-inch telescopes then, and just the biggest sees the furthest. It's all about power, really, isn't it? And how you can get the money to build them all and everything. So, but she identified this class of variables, like I mentioned, called Cepheids, and named after the constellation Cepheus, the king, and Greek mythology. The first star that did that was in the constellation Cepheus. And not only that, but she later used some sort of parallax measurement nearby stars to actually work out how far away those Cepheids were. And the graph that you can see, this was her in 1921, the year she died, 1921, 100 years ago now, be the anniversary of that. And SMC you can see that is the Small Magellanic Cloud. This is something you can see from this dark night sky in Australia or South Africa or somewhere that's south of the equator generally. And that's all at one distance. You look at this patch of sky and it's all at one distance away. So all those stars are at the same distance pretty much. So therefore you can kind of come up with a law. And this 1516 line here, she's plotted all the brightnesses of these stars against how long they take to oscillate. It's a logarithm plot. So this would be one day, I think. And this would be fractions of a day, a few hours. And this would be maybe a week or so. It's a log of the time period in days. So you discovered all these stars and how to work out the distance to them. And the last thing is she had to publish this in 1912 under the name of William Pickering. But in the very first line, he was a gallant gentleman because he said, all of this work is Henrietta Leavitt's. In the first line of his paper. Not many men did that. So lucky. There you go. That's women in astronomy history, and that actually became known as Leavitt's law, but sadly not while she was alive. So we have this structure of being able to look at a star's distance with parallax. Now, parallax is when if you hold up something in front of your eye and you close one eye. You might have all been told that. If you close one eye, you can see that hand is in front of a certain part of the background. If you close the other eye, if you can do that, your hand jumps. Basically, the Earth orbits around the sun, and you see a similar effect in stars, but much smaller. So we've got the bottom of this cosmic distance ladder is parallax, which we know for sure the stars are a long, long way away. We can see them wobbling around as Earth orbits the sun. And then you've got this other thing, she's tied parallax to this distance measurement with these Cepheid stars. So now you can go all the way to Andromeda Galaxy in distance, which is amazing. So Hubble did that. He used Leavitt's law, applied that to his variable star, and he came up with 500,000 light years away. But normally stars you see out there 100 light years, up to 1,000 light years maybe, which you'd see with your naked eye in the night sky. So this is definitely an island universe, way out there. So you're starting to look back in time, but Hubble wasn't really the one. It was pretty much down to this guy, I think. Vesto Slipher, you've probably not heard of him. Unsung hero, is a spectroscopist. So he discovered the sodium layer above us as well, just incidentally. But Hubble didn't discover the redshift of galaxies he used to make his plot of the expansion of the universe and conclude the Big Bang, conclude everything was expanding. Hubble didn't discover that at all. Hubble just found this variable star and said that's an island universe. This guy, years before Hubble, again, 1912, with a 24-inch telescope. Hubble had a 100-inch. This guy had a 24-inch telescope at the Percival Lowell Observatory in Flagstaff, Arizona. Somewhere I want to visit when I went over. I never got a chance. And he discovered that in this galaxy, it actually was blue shifted. And he'd found a load of other galaxies, red shifts, and he said, oh, that means this red shift and blue shift means space and light or something is stretching. They're moving away from us like a Doppler effect with light. So he could see that all these galaxies all together had certain kind of movement away from us, and he saw the expansion movement of these galaxies. The smaller ones tended to be more redshifted. So took someone else to highlight the significance as well, but he was an excellent observer. So this is a picture of the redshift. So if you see a spectrum of light, if you split up your galaxy's light into the rainbow of colors, some of the lines will be in a slightly different place than where they should be. And yet they're the same elements and substances causing those lines to be there, yet they're in a different place. The only conclusion is the whole thing is flying away from, sometimes at 1,000 or 2,000 kilometers a second. It takes that sort of speed in order to have a noticeable Doppler shift in his day. So he came up with these Hubble used this data with his permission, obviously. All scientists worked together. So that should be 100-inch Hooker telescope, sorry, and a 24-inch refractor with a lens at the end. That must have been one heavy lens that was 22 feet across. That was a lot of glass at Flagstaff. And they put their data together, and then Hubble looked at these variable stars in the galaxies, and they worked out all their redshifts, and they plotted them, and they realized they were all falling on a line. And that became known as Hubble's law. I guess because Vesto Slipher didn't have Slipher's law, Hubble, put the two together. So upon hearing that, Einstein is still around. So Einstein is like, here's my equation. Why did I put this lambda term in? Ich bin ein Dummkopf. Mein größter Fehler. It was something like that. These aren't actual quotes from Einstein.
Brilliant, brilliant.
There we go, Einstein with the hair as well. He took that straight out of his equation. He was like, why did I put that in there in the first place? Just because I listened to all the scientists and they all told me this. I should have realized there were actually other people. So Hubble and Schleifer showed that the universe was expanding. He didn't need that term to push his universe apart in his equation. So he shortened his equation to a much tidier solution. In fact, you can combine the left-hand side to just r minus half r, and you get just as good and a smaller equation. But there was another couple of scientists, Friedman and Georges Lemaitre, who showed that his original equation, actually with the lambda thing in it, was unstable. So it would have led to like collapses, and the whole thing would have accelerated or shrunk to nothing. So it was an unstable equilibrium, his previous equation, and he should have really known that. That's why I think he was particularly gutted, because it was against the normal laws of physics. So that's very, yeah, that's very eine dumme ich bin, or something he would have said. So then it comes on to looking at this lovely galaxy Andromeda. This is one of the Society's images that have been taken. This is Pete's image. It's quite a nice wide field. Beautiful, smooth shot of the Andromeda galaxy. And this thing is much bigger than the moon in the sky. It's a lovely thing to look at. The distance Hubble came up with was 500,000 light years to that. He wasn't very accurate at all. Hubble, the hero of astronomy, who had a space telescope named after him in 1990, he was really inaccurate. The first, in fact, estimate the distance to that galaxy, based on all the other work people have been doing, was Ernst Öpik. You know, you heard of Lembit Öpik, or OPIC, people call it, Lembit Öpik, the Lib Dem MP, who married a cheeky girl, didn't he?
Cheeky girl, brilliant.
Yeah, that guy who was trying to be cool, wasn't he? Very much wasn't. He should have just stayed, kept in his character and been true to it. Wannabe celebrity. Anyhow, his granddad, Ernst Öpik, had already got the distance as 3 times that, 1.47 million light years away. So that's 3 times what Hubble had the year before Hubble did it. And he based that on rotational movement of the stars. So it was sort of really. And Hubble then came up and said, no, it's only 1/3 as far away. So that's only 500,000 light years based on my CFIDs. But he got the wrong CFIDs. Anyhow, 6 years later, he was trying to crawl back and try and realize, maybe my CFIDs were a bit inaccurate. Nearly 1 million then, I'll go with that. Anyway, come to 1985, the Greenwich Guide to Stargazing, which was my book that got me into astronomy, they realized it's 2.2 million light years away. That's what they thought in 1985, compilation of all the techniques. So Hubble was looking pretty rubbish by this point, yet they still built and named a telescope after him. This isn't a diss Hubble talk, though, sorry, he did quite well. 2005, the latest value was, based on these techniques over here, was 2.5 million light years away, 2.5 million light years. And that's what people agree on now. And so it's actually a lot bigger than people realize. It's bigger than our galaxy, in fact. When you look at that, it's amazing to think there's more stars in that than our own galaxy. So the cosmic distance ladder, we needed a way to make that distance ladder go further. So these things, this artist's impression is of a giant, red giant star, or just any star in the foreground, and then not necessarily in the background, a very small star called a white dwarf is that super hot white thing there. And they orbit each other, and they start going close, spinning closer and closer until they get to a point where the white dwarf is so dense that it sucks matter off the other star. When it reaches 1.4 times the mass of the sun, if it can get to that mass, all of a sudden you have an almighty, mighty explosion, unimaginable brightness. So you can use that to build up a distance ladder that goes all the way out to the most distant galaxies, 7-10 billion light years away, going right back in time. And you can really that's why this ladder is crooked, because I'm trying to highlight the fact that you're stitching lots of bits of ladder together. And it took quite a while to do that in paint shop, to come up with a crooked ladder, but I think it looks all right. And that sort of gets across the impression you're trying to strap one ladder onto the next ladder and go a bit further, crawling out across the ladder, saying, yeah, it's this far away, I'm sure. So you need to reinforce that distance ladder. So there's the parallax idea of the Earth's orbit, and looking at our nearby stars, and yeah, they move a little bit, right? So we know how far away they are. That's based on how well we know our distance from the sun. Then you've got the Gaia telescope, which goes and measures these things really accurately. So a lot of you know about that telescope. So we've got super accuracy on parallax. Then we've got other sort of parallax, which uses spectroscopy, like spectral types of stars. And that can be called parallax. It's a sort of pseudo parallax measurement. And then clusters of stars, you can see they move together, and you can then use them to work out how far away they are. They're all the same distance. Then you've got Cepheids, which Hubble used, and and that highlight there, the Large Magellanic Cloud graph has appeared. Now, this top line here is the normal Cepheids that Henrietta Swan-Leavitt measured. This is how long they take to oscillate in days, and then this is their brightness. So you can then read off their brightness, and then you can infer how bright you see them. From how bright you see them, how bright they actually are, how far away they are. So how much the light is attenuated as it's travelled. And that's what you're using with the Cepheids. That's what Hubble did. That's Leavitt's law. But you can see there's all these 4 different types of Cepheids. And that's why Hubble got it so wrong, because he was looking at some of these Cepheids and not these Cepheids. And he got his distance completely wrong, because these ones are actually a factor of 3 or 4 out from these. So you'll get your distance completely wrong. That's why he only measured it as 500,000 light years. And yeah, this Large Magellanic Cloud was where these Cepheids all were taken. All of these dots are from the Large Magellanic Cloud, which is a galaxy that we can see. And we know exactly how far away that is, because it had a supernova in 1987. And they looked at the light echo from that, and they realized the light echo is going at the speed of light. Therefore, we know how fast that is, and we know how far away it is exactly. So we've got a really good ladder now. You've got other crazy techniques like looking at planetary nebulae light, and something called a maser, which is like a laser with microwaves around a giant supermassive black hole. And a Tully-Fisher relationship is just a couple of scientists that have studied the sort of dynamics of galaxies and realize how, just way to tell how far away they are. And then you've got this supernova thing, which they're always the same brightness, and so you can tell how far away they are. And then you've got the redshift on top of that. So you can go right back to the start of time with extreme accuracy. And this technique has, allowed the Hubble constant, which is the amount of expansion of the universe in this strange unit here. So It's just like a speed from the redshift, how far away it's going, kilometers per second. And this MPC is a megaparsec. And it sounds really nerdy. It sounds like something from Star Trek, Star Wars, doesn't it? Parsecs. And that's distance. That's 3 or so million light years, 1 megaparsec. And that's how fast something should be moving if it's 1 megaparsec away. And if it's 2, then it will be going twice that speed. 10 megaparsecs, it will be going 10 times that speed. That's just an expansion, way of describing an expansion. That's called h0, and that's the Hubble constant. And so it's come all the way down from crazy numbers in Hubble's discovery period, 500 or 600, with a massive error bar on it. And in the year 1960, we were getting down to 100. And then you've got all these, the boom in research and telescopes and everything in the 80s. And eventually, if you keep going, it does that. And we're starting to get into a new regime, which has told us that the value based on this cosmic distance ladder is 73.24, plus or minus 1 and a bit. That's pretty accurate for something that you're, billions of light years away from. Now here's the second equation. Oh, and it's a beautiful equation, this one. Yeah, it's just amazing. Now I could explain it. It looks really, really complicated. This bit here is the Hubble constant. That means the velocity of change in radius of the universe with time divided by the radius. That just says the Hubble constant is an expansion, which I was describing to you. And if you do the Hubble constant squared over the local Hubble constant squared, you get all of this kind of crazy stuff. The R stands for radiation dispersing through the universe. M's the proportion of radiation in the universe times its radius to the power -4. And this bit's the proportion of matter in the universe. And this bit's the proportion of dark matter in the universe. I think. And this bit is the proportion of dark energy, which is the lambda in Einstein's equation. And we're like, okay, so this guy took Einstein's equation and used the lambda and put it in another equation and worked out what we would see in terms of the expansion. This is the Friedmann equation. Basically, the universe has done this over time based on these equations. The expansion from the Big Bang here, it's gone, and this is like a kind of timeline of the universe, with it expanding as you go, this way, as it's getting wider and wider, the universe. And we're kind of living here somewhere in the middle of this dotted circle, and this is what's going to happen when the universe accelerates. So it's sort of curving outwards and expanding faster. At this point, this is the crux of the talk, the difficult bit to get your head around. I mean, never mind that equation looking like it does with all those crazy omega terms and powers in it, things. Just to get your head around how it would look like from our perspective going back. So right now we measure h0. That's what we call the Hubble parameter now. The Hubble constant isn't constant. The Hubble constant varies massively over time because the universe was a lot smaller back then. And so the radius was different. The Hubble constant was different. Hubble h0, that's when you put a naught after something, it tells you what it is now, or a kind of reference point, and that's reference to now. So everything is reference to now. The actual Hubble parameter is that just an h on its own. Anyway, if you look back, so this is a kind of slice of us looking out, look back time it's called. And if you look 1 billion light years away, you see about this far, this distance. If you look 5 billion light years away, you see this distance, just the edge of where the yellow is there. And then you start getting very, very redshifted, where the color actually changes of objects. So you get the 8 billion light years, and it seems to stretch out, and really, really stretch out until the galaxies turn into little red dots, and you can barely see them. And then there's the dark ages. When you look right back to almost the start of the universe, let's say the universe is 13.8 billion years old. And that's why I put this cosmic microwave background radiation here. There was a dark age where everything was just collapsing before any stars ignited. And that's the bit that the James Webb Space Telescope is going to be looking at. So we can understand that era even more. So it's quite complicated to go from expansion equations to what it actually looks like in our sky. And the fact that we've recently discovered that there could be a lambda means that this bit will stretch near us. It will start stretching out and pushing, an acceleration. So this acceleration here, where we are, would correspond to an acceleration here, pushing all of this wedge further out, if you like. It's quite hard to get your head around, but a lot of times you just got to trust. So these are the mad equation. I'm definitely not going to explain that, but it just means the universe is doing this over time. So, and also I thought, well, I've got a nice picture. No, I haven't got a picture of Friedman. I decided not to do an impression of him. And also what he's telling us is the universe is flat. So I've got universe, right, just finding where I am now. So yeah, the geometry of the universe, we can look at the Big Bang radiation and everything we know now, and it seems like the universe is in this category, flat. So if you went a long distance, the actual physical geometry of space is flat, and it's been measured and inferred. And if you did a triangle and you turned, through this angle, all the angles would add up to 180 degrees. Basically, if you're on a curved universe, an open universe is this one, a closed universe, it would be like the angles are greater than 180 degrees, because you can imagine a path on the surface of Earth where you turn 90 degrees there, you go down around Earth, turn 90 degrees there, turn 90 degrees, you've added up to 270 degrees. And in fact, space could be like that, but we've actually inferred that it's flat. Now you can tell, if you assume that from the measurements that the universe is flat, then this is again another sort of plot of what will happen to the universe. It's a bit like my little drawing of the universe expanding and accelerating up here. And this red line seems to fit the profile of where our universe is going in the next 10, 20 billion years. And this is just to show you the Hubble law. Basically that a straight line, if we use h0, that's the slope of this, how much the universe is expanding up there with time. And so if you apply this h0 constant 73.2, you draw a line backwards in time at that slope, you end up, in fact, with a time. And if you assuming a flat universe and constant expansion, we get Hubble time, and that time it comes out as 4.2 times 10 to the power of 17 seconds, which is 4 with 17 zeros after it, and that is 13.5 billion years. So it works. It works. You can actually look at Hubble's constant and just go, oh, just do a bit of unit conversion and come out with the age of the universe, which is amazing. The units are kilometers per second per megaparsec, and a megaparsec is a distance, not a time or anything. And kilometers is a distance as well. So in fact, the distances cancel out, and you just end up with time in the equation. Yeah, that's maths for you. I love it. Along came this chap, and this chap was brilliant. Fritz Zwicky is a very cantankerous character. He's Swiss-Czech parents. He's born in Bulgaria. He spoke Swiss-German. He emigrated to the US in 1925. He's a very strong personality, a very strong actual chap. You know, he did weights and went running and physically strong. And he worked on the big telescopes in America. And he, in fact, married somebody of wealth in about 1940s, 30s, 40s. And he used her family's wealth to buy, to make one of the biggest telescopes. And then he divorced her. I'm just saying that's the order in what things happened. Who knows? I mean, it's presumptuous of me to go into details, but and then he married somebody else that had more children. So it might tell you something about his character. But what really told you was what he thought of the Walter Baade, the German who discovered loads of things about cosmology and stars and everything. In fact, there was probably like 10 different areas of astronomy research, Walter Baade. One of them is a window you can look through in the Milky Way in summer. It's called Baade's window. He accused him. He had to work on the same corridor at Palomar Observatory. He accused him of being a Nazi, seriously, really, and threatened his life because of it. And so Baade actually refused to be alone in a room with him, even though Baade was quite a strong character himself. But the thing with Fritz Zwicky was he had a popular catchphrase. And he's a spherical bastard. It means he's a bastard whatever way you look at him. That's how I imagine he sounds. Enough of his personality. He discovered dark matter. So there you go, there's dark matter and dark writing for you in 1933. And that was a big moment in the universe. He didn't really discover it. He coined the term because he measured some missing mass in the Coma cluster of galaxies because it wouldn't fit with how fast it was they were moving, because by then they were measuring redshifts within galaxy clusters and things. In fact, it took quite a lot later for another woman scientist, Vera Rubin, to come along. Now, her history is just as interesting as Fritz Zwicky's. So he conjectured the dark matter. Vera Rubin actually proved it existed. So, I mean, he came up with some evidence for it, but she actually measured in 1965 the motions of stars and galaxies, and realized that they did this instead of this. If you did, a lot of people show you this movement in the form of a plot of how the velocity, the speed of stars as you go out. And basically the speed is just constant. They're orbiting a bit more rapidly here because they're closer in, but the speed is constant. That doesn't fit with normal gravity, not even Einstein's gravity. So you have to have massive dark matter halo, 6, sometimes 10 times the amount of the mass of a galaxy, including all the gas and everything, just for the velocities of the stars to work out with the normal equations of gravity. Vera Rubin was rejected from Princeton and Harvard. She later ended up getting into astronomy somehow. She measured galaxies' motions during a master's in 1951. And she showed there was an anomaly back then. So this is 14 years before she actually got recognized for this. So that's 14 years of wasted time, maybe. But she tried to present the paper while she was pregnant in 1952. And she got rejected. They didn't want a pregnant woman doing a talk. And it was the paper, anyway, the paper was considered controversial. So it got ignored. And so it took 14 more years and many kind of battles. So she's quite a strong character to just keep going. And she actually needed to use the 82-inch Palomar telescope to take spectra of galaxies to prove Spicky's dark matter theory correct. And she even had to create a woman's toilet for herself, which she was allowed to do. So yeah, it's a nice 2003 animation that I got. So anyhow, so this is what dark matter looks like. It's a simulation they do. So in the 1990s, computers were getting good. You could simulate this dark matter right back at the start of time. So Z is the redshift. So everything is 20 times stretched, longer wavelength than, so light is has a wavelength of half a micrometer. And this radiation, if you looked at a galaxy, has a redshift of 20, which you can't do because there aren't any. It would be redshifted to 0.01 millimeters wavelength, or 10 microns. Anyhow, it'd be 20 times bigger wavelength. So that's the sort of way of defining redshift. You don't need to know. But they can compute using a sort of, if you watch a fixed box universe that's actually expanding, but if you assume shrink everything down, then this is what happens over time. So I managed to find an old ESA animation of dark matter, and you can see what it does over time. So this is the dark matter, not the visible matter. This is just the dark matter in the universe. And crucially, it's cold dark matter, because that's not, it doesn't work if the dark matter is warm. By warm, we mean high temperature, and we mean the particles are flying around. So if you just watch that again, just to kind of see that it's come from this kind of diffuse, wishy-washy, smeared out kind of across the universe, to making these clumps and clusters and strings and filaments and things. And it's those filaments, because there's more mass in the dark matter than there is in our normal galaxies, our stars, us, everything. So that's where the galaxies are all going to grow, along those lines. And that's exactly what we see, this pattern across the universe. And the units there are 50 megaparsecs divided by the Hubble constant. Shows you the Hubble constant is changing over time. Yeah, these guys, I've got one of them here. Hi, I'm Saul Perlmutter. It looked for real like there was some mysterious repulsion. We just couldn't explain it in any way. And it's kind of like this speaking. This chap, Saul, and Brian Schmidt and Adam Rees, they discovered dark energy. They discovered the lambda. They put the lambda back into Einstein's equations, the one that he'd been horrified that he'd put in. And it's almost like Einstein's biggest blunder had been undone. And Einstein was really the true genius, again, that he was for publishing that. I think it was just chance that that happened. But no, this is weird. It's still a bit controversial. Based on this data, they got a Nobel Prize. You can see this line is supposed to be curved. and it's supposed to be, these are all the different theoretical universes and things on these different lines, and I don't think you can use that data to tell one from the other, really. They all kind of fit on all of the lines, because there's a lot of errors in these data. This is using the supernovas, and this is when they all started as their subject. They're looking at these little flashes in the early universe, but now you can get the error bars right down and to decide that actually this acceleration is real. And if the universe was a kind of a normal universe, didn't accelerate or anything, it would be down here, green zone. If it accelerated always, whereas now it's accelerating now, but not in the past, then it would be up here. And I think they're quite definitive with their data these days. So I think they've been kind of, allowed to, have that Nobel Prize, I think, which they got in 2013. Now, this plot is how much dark energy or acceleration there actually is in the universe, as proportional to all of the energy or matter in the universe. Einstein said energy was equivalent to matter, so you can plot the energy and matter all on one pie chart. The bit where we are is in this 5%. The dark matter that Fritz Ricci came up with in the 27% there, and all the dark energy, the repulsion energy, is in this sector here, and this is growing. I mean, this will actually eat up these over time, because this is growing as a proportion of the universe, which is why the acceleration has just kicked in. And they called this model lambda CDM, cold dark matter, and that's led to the development of the lambda CDM model of the universe, which everyone uses, and it's given Einstein his credit back, really. It's based on a lot of things. There's several things that prove dark energy exists, as well as just the supernova data. So we're really fairly sure that that's what happened to the universe over time. So some scientists are like, well, this sounds a bit strange, this lambda. Why is there this repulsion? Why is there dark energy? As soon as it was discovered, 97, 98, 99, people are thinking, what's doing the pushing? Why do we have to add another dark thing to our universe? And this guy, who's a string theorist, said that the following is Lenny Susskind. His lectures are great. Here we go. So the thing is not so much that this repulsion exists, but it's how small it is. So quantum physics, which is his area, predicts a massive repulsion in the universe, in the fabric of space-time. There's a huge amount of energy there, according to quantum theory. So you would expect a little bit of expansion, at least, but you can't explain why it's so small. So we measured this expansion. We give it a number, and you can write it down as 1 × 10⁻52 per meter squared. That's the units, SI units of this number, and that's what we measure. We measure that quite accurately. Quantum physics says it's supposed to be 10⁻+70. So comparing these two numbers, one has a 0 with 52 other zeros, and then a 1. That's how small it is, unimaginably small. And then the quantum physics says, no, it's supposed to be 1 with 70 zeros after it. So quantum physics has a lot to answer for. So that's something like a factor of 10 to the 120, 121, 122, something like that. And it's the biggest, most embarrassing failure in the history of science. But it's still good science. It's still good science, because it's accepting what the theories are telling you. It's being honest. it's being honest and open about it, and that's a good thing about science, I think. So, good old Lenny Susskind. Now we come on to this cosmic microwave background, and we've got these two characters, Wilson and Penzias, that discovered this hiss in this radio antenna behind them. Now, Arno Penzias, he became fairly kind of, when he discovered this hiss, wasn't a background noise, but it was actually real, and it's coming from the creation of the universe. This was the discovery of the Big Bang, remember? It kind of dawned on him that the creator was speaking to him. And he said, I think as Psalm 19, the heavens proclaim the glory of God. This remnant of the greatest explosion of all time was revealed when we realized that it was the hiss on our antenna. There's Arno Penzias. I think he died in about 1990 or so. So we're coming up to the modern day, and that was their map of the hiss in the sky. And we've since got the better one with all the fancy colour, which are these. And now we can really start looking at this hiss because we've sent up several spacecrafts. There's a Japanese one in the 80s called Kobe, Cosmic Microwave Background Explorer. Then we had WMAP, and then Planck, one just called Planck, after Max Planck. And so they've analysed these, this is the one half of the sphere of the sky and the other half here. Analysed this for structures and ripples and things based on spherical harmonics. I know you won't get what that means, but there's a picture of some spherical harmonics. Basically, they've looked at the whole universe and how the whole thing was oscillating. And you can tell a lot from it, surprisingly. You can also tell, how big they are. You can tell when, the seeds of the matter, how much matter there was, how much dark matter there was, how much dark energy there was. There's an amazing amount of things when you look at the structure of these, the ripples. And this is a picture from Planck, I think, or WMAP, of the microwave background, is that oval shaped thing you saw at the start. And you can have oscillations in it as it was being released that came from baryons doing various things. And they've analysed it using these cold and hot spots model, and they match exactly the structures of the galaxies around us. So these pictures are like mapping the distance to loads of galaxies all around us in the universe. These are all, each little dot is a galaxy, and they form amazing structures. And these are the same shape and size structures as you would expect from the ripples in the Big Bang. So you think, wow, galaxies tie up exactly with our understanding of the Big Bang and how the galaxies formed. There's another picture of the Planck data, which looks fantastic. And zoom. This is obviously false color, it's microwaves. And in fact, the microwave changes here are very, very subtle. 1 part in 10 to the 5. This is a graph of the analysis. That's, getting far too technical, really. But this is how good the data fits the model, just to show you how well it's understood. Where the data gets big here is not because we can't measure it well enough. You can measure it as well as you possibly could. The reason these are a variable is because we don't have several universes to take a statistical sample from. We've only got one universe, so we're stuck with those error bars forever and ever. And we will never know what they tell us up that end. But the amazing thing is over here, these fit the data incredibly well. Just to show we understand, So you've got like these critical densities you can extract from this radiation. And density in physics is given this funny curly P rho symbol, which is just how much mass you've got in a particular size. It's like how heavy something is, if you like. And yeah, the universe now, on average, has 5 protons worth of mass in every cubic meter. That's the critical density for our flat universe. Now, the bit we know about is called the baryons. That's our bit. We're baryons. We're made of baryons. That's called omega B. And that's known as 4.9%. That's 5% roughly of the universe. This is the same as that pie chart, really. The radiation, all the stuff that's flying around, that energy is a tiny portion of the, and the dark matter, this you can get all from the radiation. 26% for dark matter, 68 and a bit, maybe 70% from the dark energy. There's more. This also tells you there's more dark energy, dark matter, than our humble atoms and normal stuff. It even includes neutrinos, particles like that, and they all add up to 100%. That tells us the universe is flat, and the geometry of the universe must be flat. You can also, crucially, get Hubble constant from the cosmic microwave background. So now I've built up to it for the last hour or more. Wait, wasn't that supposed to be 72, 73.2? And this is telling us it's 67 plus or minus about a half. And they don't match. So from the cosmic distance ladder, we get that. Now I thought everything else was matching, the structures, the understanding. We were going right along our theoretical paths from 2 different angles, and suddenly we can measure so well, we've got a disparity there. So 67 and 73, they sound like roughly the same number to us, but if you know you can measure them that accurately, and they are considerably different, that's called a 5 sigma difference there. That's 1 in 3 million, I think, chance. 1 in a 3 million chance that they just happen to be that different. And that's the crucial level when physicists, not cosmologists, when physicists say, I've discovered a particle or something like the Higgs boson. So there really is something weird going on we haven't understood. And yet at each stage along that distance ladder and the Big Bang, the fantastic Planck satellite, we've got a crisis. That's our crisis. That's the crisis in cosmology. Okay, it might be a bit of a letdown after all of that explanation, I don't know. But to physicists and astronomers, this really does seem like a crisis. It's like, yeah, sorry, I'm jumping ahead there. But yeah, so this gap has been growing. And so everybody's piling in with all of their different measurements. And there aren't really any independent measurements that you can do that tell you anything. In fact, the only other way is you know those gravity wave detectors, the LIGO and the Virgo, they're called, and big L-shaped things, 4 kilometers long, and they've just started detecting black hole collisions. And a couple of years ago, they detected a neutron star. 3 years ago, a neutron star collision. And then it turns out neutron star collisions, gravity waves, is a completely independent way of measuring the Hubble constant, the expansion rate of the universe. And there's a pair of neutron stars coming in. You can see the ripples in the background. They're the gravity waves distorting space-time. And that's them exploding in a massive, massive supernova and forming a black hole. So this is the third way. This is what we really need to do to kind of restore. And we have already made two now measurements of neutron star collisions, and there's some other stuff you can use. There's a picture of a LIGO. This one's probably Louisiana or Washington. Washington State is usually the one they take a picture of. Two big vacuum chambers with 5 sets of suspended springs to keep things from vibrating, and lasers shooting down down there and back, and down there and back, and coming back and interfering here and revealing vibrations in space-time that are smaller than 1,000th of the diameter of a proton. And this is regularly detecting things. Absolutely incredible. This has come up with 70 plus 12 or minus 8. That's really the least helpful number. It's right in the middle, 73 and 67, and it's right in the middle. And it's saying, oh, really, this 1 in 3 million chance, and yet it's just in the middle. How can that be? And people have tried to apply different methods like baryon oscillations to this, and they came up with that, which is it's agreeing with the microwave background than it does with the cosmic distance ladder. And this woman here is looking at star evolution, red giant branches, and she's actually used telescopes such an incredible amount of data that she can work out Hubble to quite a good accuracy, and that is also the lower. It's now coming out. She originally was up in the 70s, but now she's decided to go with the 67 value. So she's coming along towards the cosmic microwave background value. Yeah, so the latest situation is we've got loads and loads of measurements. So these are the numbers. This is a Hubble constant of 67 here. There's 70 on the bottom. And there's the 73 point something up here. These are all the 70s. All the different papers that have come out going down there, all the different methods of measuring it. So how do you explain that difference there? Because there's a whole group of them that look at the indirect microwave background radiation there. And there's a whole group of them here that come up. I mean, admittedly, some of these have got huge error bars on, so you at least you wouldn't count them as much. But there's basically a confident band here and a confident band here, and they do not meet. And this is now getting to the point where, if you combine all of this knowledge, you're getting to 6 and 7 sigma differences. So what do we do? Do we just choose one, or do we go, oh, we try and bend the others down? What's wrong? And we've understood everything to such extreme accuracies. There was another guy actually. You need to. So yeah. So just before I bring him in, around the corner. So why do they do it? It could be systematic things. It could be like unsuspected unknowns that are creeping in. Here's a picture that I tried to take of a gravity lens that wasn't there on our 20-inch telescope. It could be how does that calibration that we've used actually apply? It could be something about that, another systematic sort of error. It could be like that. We're such at the limits of measurement that we're fooling ourselves somehow into believing the errors are smaller. And it could be just we've assumed something wrong. And so, so this guy, Subir Sarkar, we've got here, he's done a great interview on, well, it's at Oxford. So he's called some of these assumptions into question about dark energy, not about this crisis in cosmology, but he doesn't really think dark energy necessarily exists. he thinks the supernova data need to be reanalyzed. And he says, the supernova data were all corrected based on the lambda CDM, and we have to remove that assumption. That's roughly what he sounds like. And he thinks H0 should be 68 rather than 73. So yeah, he would agree with the lower end of things. And that's a lot of observational astronomers agree with the upper end, and I've tended to come down towards the lower value. Because he didn't assume that this lambda CDM model. He's had to actually take that off the data and start again. And he can't really find much evidence for dark energy. Well, so it's still likely that it's there, but he can find this strange thing. It's like a dipole across the universe in the cosmic microwave background. People are assuming isn't there for some reason. But he reanalyzed the cosmic microwave background, and he's saying, look, this dipole ought to be there because we're, there's something going on around us that we don't know, but there's a great movement, or there's a void, or there's a flow, a dark flow, or something. And he's looked at the galaxies around us for that dark flow, or void, or movement, or something, and he can't see it. So it's something mysterious beyond our sphere of measurement that he thinks, there could be something there that is affecting all of these measurements and could potentially explain, But then everybody's trying to do this. He's just particularly good at it, his mathematical analysis. And to be honest, it's quite difficult to get into without understanding and being a scientist. You wouldn't be able to argue with him. And yeah, so he believes this is dipole, which is like assuming we're moving in a particular direction or something like that, is real. Or it could be, if it wasn't the measurement being wrong, new physics. That would be great, wouldn't it? If there was something new. So this sort of symbol here is something different about the expansion, this dark energy, this lambda in the equation, Einstein's lambda. We now have another parameter called W, which is it should be -1, I think, and it's how dark energy changes with time. And we would think it would just be but we're completely assuming this W is exactly -1. It doesn't have to be that. If it was slightly different, that would actually explain this discrepancy. But why would it be 1.2, well, when it should, according to most sensible theories, be exactly 1? How on earth could you explain a 0.8 or 1.2 when it's so close to 1 that -1 that again, we're assuming the universe is going to be kind to us, aren't we? So the other thing it could be is that a sterile neutrino. And if sterile neutrinos were released in the early universe, they could couple with some of the particles. In fact, there's a couple of observations of some big particles that we've seen in Antarctic ice. With a fantastic experiment down there that could be new forms of exotic matter. They might explain it. There's all sorts of, you can get into crazier and crazier theories, but this W parameter is assumed, and the sterile neutrinos are assumed not to be there because why would there be? Dark matter could decay, as Roger Penrose thinks. This weird Fritz Zwickie's dark matter. It's stuff that you can't even interact with. It's not just dark. You can't even. You'd go through it. It's transparent matter, but with mass. So that could decay over time, and then that would change the whole expansion history of the universe. So I'm just going to leave you with a picture of some dark matter with your own thoughts, really, and hopefully this will inspire a few questions. The one way we will solve it, I think, one way or the other, is look at the future LIGO data. And unfortunately, LIGO shut down with a pandemic last year. So I'll leave you with the trace of the first neutron star. And you can actually hear the sound file of this. It kind of goes whoop, in real time as these neutron stars spin together like that. So we're just hearing the last few seconds of that as sound in gravitational waves. So if we measure 50 of these, which we should be able to do in the next maybe decade, then we'll know one way or the other. But until then, it's anyone's guess. So hope you all survived that, and you can all unmute again. It's time for questions, and I have no idea what the time is. I probably seriously overran. So thank you for.
Thank you very much.
Well done, very good, Dan. Yeah, covered everything.
Yeah, so yeah, fire away. Even if they're questions about or comments about terrible impersonations of people.
One for me, Dan.
Yeah,
Yeah, I guess, Dan, the Hubble figure, why it's so important, I guess, is because it determines the age of the universe, right?
yeah.
So the 13.8 billion years that we're told all the time, which Hubble constant was that based on? Do you know?
Oh, the 13.8. Well, actually, it's based on the lambda CDM model. That you have to allow for the slow acceleration and or the Freeman equation and everything. It's quite. It's not just a straight line, but it's based on the 73, the 73 one, I think. But the age of the universe is literally unknown. Some people say it's like 14.5 billion, and some say 13.5. If you use the 67, you get 1. And if you use the 73, you get an age. Obviously, like you could guess by sort of stellar evolution how long stars are supposed to live, and you could sort of work out theoretical age from that. Yeah, and yeah, that's science for you.
Yeah. Dan, I put a question up on the chat. Maybe I should read it out if that's all right with you.
My screen was I can't actually see.
No, well, if I read it out,
Yeah.
I think you touched on it right at the very beginning, and I just need to be clear on it. What we see today as a relic of the Big Bang is the cosmic microwave background radiation.
Yeah.
Now, if that's been red-shifted over the vast distances with the expansion of the universe, what would be the electromagnetic radiation at the start? Are we talking gamma rays, X-rays?
Oh no, it's a black body radiation equivalent to at the time of emission of something like 3,000 Kelvin. I think slightly over 3,200, 3,300 Kelvin, or 3,000 degrees C, which is the temperature of an incandescent light bulb. And it correlates with roughly with the temperature of a flame, which is usually, flames are usually about 2,000 degrees when you measure them or so. And it's the point where particles, that atoms form, basically, when the nucleus and the electrons combine to make stable atoms that can then absorb, with an electron jump, they can absorb the radiation. So the radiation is free to go, and they can kind of collapse and start absorbing that energy, and it can become dark. The universe then becomes dark, but with a background radiation that then drifts out. And it's the plasma temperature. We can easily create that with a blowtorch. You get an oxyacetylene blowtorch, it reaches 3,000 degrees. which is quite interesting, really. Yeah, so something like that. Visible light. It would be a kind of yellowish white light. Temperature of a cool star, maybe.
Well, if that's the case, then it hasn't redshifted all that distance,
Oh,
then,
no,
has it?
so that's the temperature it's emitted at. It's redshifted by a factor of 1100 into the microwaves now. So the expansion of the universe is now 1100 times bigger, and the thing is redshifted by a factor. The wavelength is 1100 times longer than the wavelength of light that was originally emitted. So that's why it's microwaves. It's the sort of millimeter radiation, which is something you know a bit about, a bit more than me, actually, don't you?
Well, yeah, see, I'm a little puzzled when I look at these diagrams, because there's lots of diagrams that show you the evolution over time. And the cosmic microwave map is always shown immediately after the Big Bang, when I would have thought that that is what you see at the other end in the present day.
Yeah, and we're seeing microwaves now, but the thing is continually going to be visible in the universe, because you're always going to see it from a further and further distant horizon, more and more redshifted over time. It's the same radiation, it's buzzing around, it doesn't escape the universe. We're seeing the stuff that's 13.8 billion light years away, behind all of the stars. It's at that distance from us. It's actually been redshifted by that huge amount. So the microwave radiation we're seeing the stuff that's 13.8 billion light years away from us. That's what we're seeing. So you'll always see as a background. That's why it's called background. So yeah, we're still seeing it now, which is obviously an amazing discovery. But that was emitted 380,000 years after the Big Bang, wasn't it? Because it took the universe that long to cool to the point where atoms could form from the plasma. But yeah, amazing how much information it contains. So I tried delving into some talks, some lectures on that, and it was really heavy going maths, which I didn't follow. What you can actually get out of that microwave background radiation. So it looks like it's coming around to that 67, 68 sort of figure, isn't it? From my guess anyway. But if we have a survey and everybody types in 67 or 73, let's see, and then we'll submit that to the scientists. Survey, 20-something people, 24 people in Breckland Astronomical Society, and 68, that's your guess. We can take bets, and when in 2030, when the neutron star collision data hopefully come in, we'll see who's the closest, and it'll be a decent prize. Yeah, that'll be a bit fun for those of us that are still, if Breckland is still running by then.
I could probably get a bookie to take you up on that.
Yeah, probably a good bet, isn't it?
You'd have to give error bars though, of course.
No, we'd all submit a precise figure to like TDP, and, whoever's closest. 42, like Maz thinks is 42. Maybe it'll come down to 42. No, I'm not giving John Culshaw a run for his money. I didn't.
The impressions are really funny.
I was just going for comedy value, as in rubbish impression. They can't really do them seriously.
You know where the 42 comes from, Dan, don't you?
Oh, of course, yeah.
Yeah, okay, then all right then.
Douglas Adams' mind.
Yeah, I say there's great T-shirts with it on.
And of course, it's the answer to the ultimate question, which is what do you get when you multiply 6 by 9? Not by 7, isn't it? Because he spells it out from Arthur Dent's subconscious in Latin.
Oh, okay.
And it says 6 by 9, and nobody picks up on the fact that 6 by 9 is 54, not 42.
Yeah, it doesn't equal 42. It's on the side of a mountain as well, Dan, I think, in the movie.
Oh, lovely. Yeah,
Talk about the ASCII code for an asterisk, which is
Is it?
universally known as the wildcard character, so it could be anything.
Wild card interruption.
Dan, can I ask a question? If time and space began at the Big Bang, what's the universe expanding into?
Good question.
Oh, well, if time and space are created at the Big Bang, in that picture, there wouldn't be any space for anything to expand into, would there? The space would just be a region with a distance independently of anything else. It doesn't have to be anything, does there? We can't conceive of it. But it's all about the limitations of our minds and our mental pictures, isn't it?
Yeah, certainly space can't expand into space, obviously.
It expands, creates its own space-time. It expands, so yeah.
It could be.
Another thing is that time may also not necessarily be a fundamental property of the universe, and it might just be a result of our perspective, our blurred perspective, which is kind of where entropy comes from, on our particular set of interesting things. So just because we observe the universe a certain way, that might be the way you have to observe the universe in order for it to have had a lower entropy at the beginning, and that's the only way you can get the arrow of time. So yeah, even time is probably not a fundamental construct, or it might not be.
And yeah, but before we go, we ought to do my original announcements, which I didn't do because I went straight into talk mode, didn't I? But rather than introducing myself, I didn't know if Andy wanted to say something about the. I mean, you recently texted me on. Did you want to? Which we were supposed to do in the announcements, the donations. Oh yeah, I'll do it for him.
Hello, no, that's fine. I am here. Thank you very much, everybody, for paying memberships and stuff. Only a couple left over to sort of collect. Getting some donations, just random donations from people, so you know who you are. Thank you very much for that as well. And our BAS 100, I had to print off some new tickets because we've sold up to about 14, so that's excellent as well. So thank you very much all.
Cheers. I thought you'd get your little bit in there. It wasn't just all me. Yeah. There you go. So yeah, you're all left in a what should I say? Hopefully buzzing with knowledge, overloaded. How would you describe it? It certainly overloaded my head for the last few weeks. Trying to get into all of that.
Well, Dan, just add some more confusion.
Right.
There's a lot of concern about dark energy, that it could be something to do with modified gravity or something, which.
Yeah, there was always
a spanner in the works, perhaps.
There was dark matter wasn't believed as well, but then dark matter became more solidly proved, and so dark energy is a sort of becoming a little bit more of a standard now, which is it's a bit annoying because I don't like it either. Don't know if anyone else likes it. It's not about whether you like it or not, is it? It's about whether the measurements say there's something there. And that's what the whole talk's about. But then measurements that don't agree. So when they don't agree, they tell you, oh, new physics. People can get busy then on a new problem. But certainly Einstein's been proved right the whole time. There's no doubt about Einstein's theory.
Yeah.
That's 106 years old this year, isn't it? Amazing. I thought it'd be nice for you to see the equations, but obviously I didn't have to find. They weren't all of the equations. It was just a smattering. It's great actually trying to get my head around what the Einstein's field equations mean, but I still don't know what's in those tensors. So it's just madness. That's why it took Einstein so long to come up with them, didn't it? Took him 15 years after his theory of special relativity or so, didn't it? Come up with the gravity one, just because the maths was such a pain. So anyhow, there's plenty of further YouTubing you could do on that. I'm sure all of those things, like even Jim Al-Khalili, Brian Cox, all their stuff.
There's a good series of lectures by Susskind on YouTube on general relativity. I think he's great. I think he's excellent.
He's cool as well, isn't he?
Yeah.
I was important to say the word schmuck, but he never does.
Well, he does an excellent, I think it's 10 or 12. They're just over an hour long each, and it's a proper general relativity lecture. And he does go into the maths and the tensors and that sort of thing. Very good indeed.
Yeah, cool. Right, I'll let you all go in. Someone wants their dinner. Yeah, do. So I managed to have mine before I came out. I'll go and rescue my laptop now.
Well, good talk, Dan. Excellent. Thank you very much.
Very good.
Thanks, Dan.
Hey, guys.
Next month we've got Paul Money back for his second one on Mars. Thanks for the clap.
I have another one.
Do our best.
An unfortunate turn of phrase, that.
Yes.
I was just going to say, Dan, that there's more than a few rabbit holes on YouTube you have to avoid. Certainly, you see some of the comments when people disprove flat earthers and Apollo hoax. You see some of the comments just sitting there trying to bang your head against a brick wall for them.
Yeah.
Invariably, the people who say they know this, they say, "Oh, we've studied relativity for 10 years. We know the Earth is flat." And you're like, you haven't studied anything.
Maybe the universe is just saddle shaped and it makes the Earth look flat. I don't know.
Or somebody who's saying the Earth is in fact pear shaped.
Yeah, it probably is pear shaped.
This notion of shape is a little bit ropey, isn't it?
Yeah.
We're on the back of a turtle, aren't we?
I know.
Oh, yeah.
Turtles all the way down, isn't it?
We're great tattooing.
So that's when he starts saying Terry Pratchett had the right idea.
Yeah. I think there's a talk in linking it to sci-fi, linking astronomy with sci-fi. That's a potential good talk, isn't it? One I'd like to.
That could cause a lot of contention as well, couldn't it? A lot of hardcore sci-fi enthusiasts that would believe technology from one series of sci-fi compared to another.
Oh God, the Trekkies versus the Star Wars. Yeah. Doctor Who versus Battlestar Galactica.
Don't forget Blake 7.
I'm not much of a sci-fi geek, really. Well, video. Cheers. Then, right. I will bid farewell to you.
Okay, guys. Thank you.
Thanks, Dan.
Cheers, Dan. Thank you.
Cheers, Dan.
Thank you.
Cheers, Dan. See you later.
Yeah.
See you, Dan. Cheers. Thank you. Good lecture.